All right, my dudes and dudettes. Today we're going to talk about the different types of forces and how, on diagrams, how we're going to represent forces. So again, just a little review from first section. A force is simply a push or pull that's acting on an object. So again, we're looking at how forces affect an object's motion. So if we have, let's say, an object moving at a constant speed, we talked about how those pushes and pulls are going to balance each other out. If it's at rest, we're going to see the same thing. And then if we see something speeding up or slowing down, that's going to represent that the forces are going to be unbalanced. But it's all about those pushes and pulls that are acting on it. So when we look at those pushes or pulls, there's really two types that we can see. The first type of force that we can see is what's called a contact force. So a contact force is literally a force that requires physical contact between whatever is applying the force and whatever is experiencing the force. So take, for example, carrying an object, pushing an object, or pulling an object. So those would be our three types of contact forces. Again, it occurs anytime there's physical contact between the two. Second type of force we have is what's called a field force. Now this one's a little bit more interesting when I'll show you some demonstrations in class, but a field force are forces that occur without physical contact between two objects. So there are some main forces that we see in nature. You guys have probably experienced at some point, but one of the main ones is gravity. So gravity would be considered a field force because there's not physical contact required in order for gravity to affect an object. So imagine I have a surface, and let's say the surface is like the earth, and I take a ball and I have it above the surface. So what happens when I release that ball, it's going to fall towards the ground, but it does that because gravity is able to pull down on it without actually making physical contact with the object. So that's what's called a field force. It creates, essentially what happens is the earth creates what's called a gravitational field, and then that field affects any other object that has mass. Same thing can be seen with magnets, and I know you guys have seen magnets before, but magnets create what's called a magnetic field based on their polarity of north and south, and those poles are going to affect other magnets nearby, whether it's going to pull them inwards, or we might see with magnets, which is different from gravity, might push things away. Same thing is true when we have these positives and negatives. These are what are called charges, and we'll actually look at this second semester, but charges create what's called an electric field. And that's where you might experience like an electric shock or that static shock you might experience in the winter. But again, these all require, or do not require, physical contact between the objects. They act over space. All right, so all forces are going to be measured in a unit called the Newton. So we, in the United States, use a unit called the pound. But in the metric system, the unit is a Newton. And the unit of a Newton really stems from what forces do to objects. So a force causes an object to simply, especially if it's unbalanced, causes an object to change its motion. So when we talk about an object, the thing that we use to analyze an object is what's called the kilogram. So remember, a kilogram is a unit of mass, and that explains that inertial property of an object, which how much stuff it's made of, how much resistance to forces it has. Versus acceleration. Acceleration is obviously a change in speed. So it's how much speed something's gaining or losing. So 1 Newton is equivalent to 1 kilogram of mass experiencing an acceleration of 1 meter per second per second. So this is what's called the Newton. So Newton is defined as mass and acceleration. We'll get to that in our next section. But all forces are going to be measured using the same unit called a Newton. Okay, so our first two forces we're going to talk about, first of all, is the applied force. So the applied force is going to be a contact force. And essentially what it is any sort of contact, a push or pull created by some external object like a person. Okay, so let's say I push, if I push a chair, that's an applied force. Or if I pull something or pull a chair, that's going to be applied force. The applied force we're going to label capital F for force, and we're going to use a capital A to represent that applied force. So I'll write it as FA. You might also see this as just a capital F, F standing for force. Okay. Next force we have is the force of gravity, or the gravitational force. The gravitational force is that field force, that pull of gravity that acts on all objects. Key thing here with this one is that this one always acts downward towards the ground. Gravity is always going to pull things downward. So here I have an example of it being on an inclined surface. Notice gravity is pulling downward. This would apply as well to any sort of object resting on a surface. Gravity is going to pull it downward. And this also applies to things moving throughout the air. Gravity, again, is going to pull it downward. Okay, we're going to symbolize gravity of this force. You're going to see it either with a capital G, or you'll see F with a lowercase g as a subscript, or you might see W for weight. Okay, now we're going to talk about this in class, but the gravitational force is actually what gives us weight. We always have mass, we're always made of stuff, but depending on the gravitational field we live in, that's going to dictate how much we weigh. All right, the next two forces we have is what's called the normal force. So the normal force is any sort of force applied by a surface, okay? So when it's in contact with a stable object. I always like to think of this as being applied by a surface. So like, for example, if I have a book that's resting on a table. As it's resting on a table, we know that gravity is pulling it downward, but at the same time, it's not falling downward because the table is supporting it. And if gravity is pulling the thing straight downward, the normal force or the support force is going to push straight upward. Okay? So we call this a support force as well because it is caused by a surface supporting the object. The word normal, okay? Normal is a fancy math word, but normal, that's normal represents perpendicular. So what this force tells you that no matter what the surface is, the normal force is always going to act at a 90-degree angle to the surface. That means if I were to have some sort of angled surface like this, 90 degrees to that surface would actually go up and to the left. It would make a 90-degree angle with that surface. So that's what the word normal means and why we use that. Okay, we're going to symbolize this force either with a capital N or you'll see F with a subscript of N. Okay, whether the N's capital or lowercase. Next one we have friction. So friction is a force that always opposes motion. And it's always, again, it's going to be a contact force, just like the normal force, but it's a contact force with any sort of surface. But it has to deal with motion on a surface. So it's whether, let's say an object's at rest and I want to push it, friction is going to act against that between the two surfaces. Okay? So I push it to the right, friction would act to the left. Friction also acts on objects that are already in motion. So let's say that I have an object moving along a surface. Friction is also going to oppose that thing in the opposite direction. So the key thing here is that friction always opposes motion, whether something wants to move or whether something's in motion. We're going to symbolize friction with a capital F for force, but with a lowercase f here to represent friction. Or you might see just that fancy little script F that represents friction. Okay, next two forces we have are air resistance and tension. So air resistance kind of goes along with gravity and things in free fall, something we talked about last chapter. But air resistance is going to be a force that acts, it's very similar to friction, but it's going to act on objects that are moving through the air. So the way to think about air resistance is think of this as air friction. Okay, so an object is moving through the air. Air is made up of molecules, so as it moves through, it is going against those molecules. It's hitting all those things, and it's actually forcing that object to slow down, so to oppose the object's motion. Okay? How we symbolize air resistance, you'll see FR for resistance, or you might see sometimes used a capital R for air resistance. Tension. Tension is caused by ropes, cables, or pulleys. So again, this tension is very similar to an applied force. But let's say I take a box and I want to move it along a surface, but instead of just pushing the box, let's say I attach a rope to it and I have someone pulling that rope. Hard to draw this picture, but I'll do my best. Let's say I have someone pulling that rope. Okay? When you use some sort of rope or cable or string, it's going to create what's called a tension force. And that tension force is going to be like a pulling force. Tension is never going to be a pushing force, but it's always a pulling force acting in the direction of that rope, string, or cable, or whatever it is. Okay? Friction or tension, we're going to label either with a capital T or you'll see FT for the force of tension. And then lastly, we have what's called the spring force. So the spring force is going to be a force caused by springs. This is one we won't see as often, but I just want to introduce it because we actually are going to analyze it. But the spring force is due to springs. Okay, so let's say, for example, I take a spring that has some length to it and I push down on it and I compress that spring so it's nice and tight. What happens then is that I press that spring down, that spring is actually going to apply a force back up on me. Same thing with these pictures. If I hang, let's say, a mass from a spring, no matter what, the spring is always going to pull back up. So the spring force is very similar to a tension force, in that it always reacts to whatever I'm doing. So if I'm pushing a spring, it'll push back on me. If I'm pulling a spring, it'll pull back on me. Okay, so that's a spring force. So you'll see this either with a capital S or you will see Fs for the force of a spring. In total, these are the most common types of forces that we're going to see. So our goal is to try and identify when in a diagram those forces are acting on an object. All right, so what we're going to do today is, and so once we understand the types of forces that we have, and we'll work more with this, but we're going to draw, essentially to understand Newton's first law and his other laws, we're going to draw all the forces acting on an object. Doing this is called a force diagram. The fancy name for it is actually a free body diagram. So free body means we're going to ignore any other object that's near that one object, and we are simply going to draw the forces that are acting on that one single object. And that's, again, viewing it as a free body just by itself. And what we're going to do is we're going to draw what are called vectors. So vectors are arrows. So a vector diagram, they're arrows used to show the magnitude and direction. So magnitude is a fancy word for size, and obviously direction is which way is pointing. Okay? So you'll see here in a little example, this box right here, this is going to be the object. Now what I'm going to use is we can either use a box, we can use a circle, we can use a dot, or we're just going to say that this box represents whatever object I'm talking about. So this could be, for example, this box could be a car. And I could say, okay, what are the forces acting on that car? I'm not going to necessarily draw a picture of a car, but I can represent the car as a box. And I can say, okay, there's an applied force pushing it to the right. I have gravity acting downward. I have the normal or support force pushing back up. And then I have friction acting against the car. And then by thinking about this, if we fit numbers to it or whatever, by looking at the direction of the arrows and the forces and considering the length of the arrow with the magnitude, it'll then give me a visual representation of whether the forces are balanced or unbalanced. And then I can apply Newton's first law and some of the other Newton's laws that analyze the forces and how they pertain to motion. So the first thing we need to do is be able to identify what forces are acting on an object. So let's say I have these three diagrams. First one, I have a guy that's just sitting or standing on a surface. So what forces would be acting on him? So if I look at the forces, obviously we'd have gravity, because gravity is always going to act on an object, and gravity is going to pull something downward. So I have gravity. He's standing on a surface, so I know there's a normal force. And when I think of the other ones, like an applied force, there's nothing pushing or pulling him. Tension force, there's no strings or ropes or anything attached and pulling him. Friction, he's standing there, he's not moving, so that means there would be no friction. Air resistance, same thing. And then spring force, he's not standing on a spring or whatever. So the only two forces here would be gravity and normal force. Okay, so then we could draw that force diagram based on that. We'll do that in our next example. But if I continue on, next diagram. So I have a girl parachuting. She's going down towards the ground. So I know again here that there's going to be gravity acting on her. She's going through the air, so I'm going to think that there's probably air resistance. I'll just write that as air res. I'm a little bit lazy right now. Air resistance, again, is like friction. You can think about, okay, gravity, air resistance. She's attached to a parachute, which creates the air resistance, but it also has strings. So if I think of maybe the forces act on her, I might want to say tension, because there are ropes or strings attached to her. There's no springs or anything like that. So again, those would be the forces that are acting on it. Then I have a car driving along a surface. So again, you're going to have gravity. Gravity is always going to be acting on an object. You're going to have the normal force because that car is driving along a surface. There might be friction because it's also moving along a surface. Heck, there's an engine. Now treat the engine as I know it's a part of the car, but the engine's actually what propels it forward, so we could treat that as an applied force. Tension, there's no ropes or cables attached here. But heck, there are springs, so maybe I can analyze a spring force, right? So we have all these different forces that could be acting on it. What we're going to do is, as we do this, again, when we draw a free body diagram, we're going to consider these forces, now use arrows to represent them. Okay, so I'm going to do the first three on the top, and then I'm going to have you guys try the last three on your own. But let's say I have a physics book resting on a table. So now we can understand what forces are acting on it. So if I think of a book resting on a table, I know that gravity will be acting on it. So gravity would be acting straight down. So I'll write that as Fg. Then, since it's resting on a table, I know that there's going to be a normal force acting on it, okay? So I want to draw an arrow representing the normal force. Now, when I do this, I'm going to draw all my forces, and why we use a box is I'm going to draw all my forces acting at the center of this box. So this center, this dot right here, is going to represent the center of mass. We are going to assume all objects, we're going to ignore the fact, like a human, that we have arms and legs that spread up, but we're going to look at all the forces acting on our center of mass. I'll talk about why in class, but again, what that's going to do is it's going to simplify the motion to one dimension, meaning we're only going to move in a straight line. But so when I draw that normal force, then I want to draw an arrow upwards. Now, because the book is at rest, here's what I need to then analyze. If it's at rest, these two arrows, and I use a little geometry there, those two arrows need to be approximately the same length. Because if it's at rest, I know the thing's balanced. If it's at rest, then I also know no air resistance, no frictions acting on it. There's no rope, so no tension. There's no spring force. And I think that's all. So we just have those two forces. Next one, I have a skydiver falling and has reached terminal velocity. So skydiver is falling through the air. So skydiving hasn't said yet that we opened the parachute, but then I know skydiving, we have gravity downward. Always going to be written there downward. Okay? We reach terminal velocity. So terminal velocity is a sassy term. When you're falling freely through air, again, there's air resistance. So what terminal velocity means is that as the gravity is pulling them downward, there's air resistance upward. I'll write that as FR for air resistance. Okay? Now, if it's moving at a terminal velocity means moving at a constant speed, which is going to tell me in this case that the air resistance and gravity are also going to be equal. This gets into Newton's first law, that an object at rest will be because of balanced forces. Object moving at a constant speed will also be due to balanced forces. Now, as a person is falling through the air, they're only moving up and down. So I'm not going to put any left to right arrows here because air resistance is always going to oppose the direction of motion. So in this case, if it's falling, it'll be straight down. Next one. All right, large crate is being pushed leftward at a constant velocity. Okay, so if it's being pushed leftward, I know being pushed leftward means there's an applied force to the left. Okay? Now, if it's being pushed at a constant velocity, here's what that tells me. A constant velocity means all the forces must be balanced. So if there's an applied force to the left, that means friction must act against it. So I'll write FF for friction. And knowing that it's moving at a constant speed, those two forces must be equal. Now, is that all the forces acting on it? So this is the one where we looked at left and right. But understand that an object like a large crate is always going to be affected by gravity. So there's going to be gravity pulling it downward. And if we're pushing it, I'm pushing a crate, I'm going to assume that that crate is on some sort of surface. Okay? And assuming it's a flat surface, I would think then that there would be some sort of normal force. And again, constant speed means that all those forces are balanced. Okay, so in this case, I would actually have four forces acting on that object, using those arrows to indicate direction and using the idea of constant speed to show that they are all balanced. All right, so what I'd like for you to do is kind of look at those problems I just did, and I want you to pause the video right now and try the next three problems on your own. Let's take a look. So diagram one, again, you might be thinking of different forces, but slider reached the bottom of the hill and is coasting rightward while slowing down. So I know that gravity is always going to be acting. If they're on a surface, which is they're on the ground, there's going to be a normal force. They're coasting to the right while slowing down. So if I know if they're slowing down, there's got to be something acting against it. So if it's a rightward moving object, then I think friction would be acting to the left. Now somebody might be saying, well, why isn't there an applied force to the right? So this goes into that whole idea of inertia. An object that's going down a hill is gaining speed. As it reaches the bottom of the hill, the speed that it gained is going to keep that speed. It's got what's called momentum. It's going to continue to move until friction takes away that speed. So objects do not need a force to maintain their motion. Okay? But you do have something like friction that could take that motion away. Okay, the next one, we have a ball tossed straight up in the air, and it says it's going upward towards its peak. So I know that as it goes upwards, it's slowing down. Okay? So I put gravity here, and then I put air resistance. So think about it in a real life situation, gravity is going to be pulling that object down. Since it's being thrown up in the air, there is no applied force going upward. After I let go of a ball, I do not force that ball in the air anymore. It's now moving based on the momentum that I gave it, okay? And then I also put air resistance here. Now, I know the problem says ignore air resistance, but I just wanted to talk about this, that if it did have air resistance as the ball is going up, this would be a case opposite to up here. Air resistance would actually be pointing downward. Now, what we might do in certain situations to help us out, like here, we can ignore air resistance just so we can think about gravity is the only thing acting on this object. So if I were to draw this again, I would simply have gravity pulling straight down, which is why as an object goes up in the air, gravity is the only thing acting on it. It is unbalanced, which is why it's going to slow down. And then lastly, say we have the brakes applied to a rightward moving car. So I have the brakes being applied if it's moving right. Brakes being applied, brakes are simply friction. It's friction between the tires and the brakes. Acting to the left then, because if a car is moving right, slowing down, friction would need to be to the left. I have gravity again, because gravity always needs to be in these diagrams. Now, if gravity's there and it's a car on a surface, then I know there has to be a normal force acting on that object. And again, I did not put a force to the right, because in a car, when you hit the brakes, you are no longer have your foot on the gas pedal, okay? So once you take your foot off the gas, there is no applied force anymore. And once you put it on the brake pedal, now you're applying friction, okay? So again, there does not need to be a force in order to keep something moving, right? In this case, yes, there might be a force in order to keep it going forward. I need to apply the gas, but if I let my foot off the gas, then the brakes would be the only force. So again, this is looking at, again, drawing these force diagrams. We identify the types of forces that are acting on them, and then use arrows to represent the size and direction of these forces, which again is going to help us to analyze whether the forces are balanced or unbalanced. All right, we'll see you guys in class. Peace and blessings. Goodbye now.